today we're going to be talking about an in-depth look at the wood wall design in RISA. My name is Deborah Brisbane, and I'll be going through both RISA-3D and RISAFloor, as Matt had mentioned. Today we're going to be going through a lot more PowerPoint than we typically do on a webinar. This is going to be very in-depth, meaning that we're going to be talking a lot more of calculations and design assumptions. So a lot of times I will be in a PowerPoint presentation, and I also recommend that you probably download that PowerPoint presentation at the end of this presentation, so you actually have a way to go back and look through it and think through it. There is a lot of material to be covered, and it will take a little bit to absorb it. So let's start out here by talking about the programs we're going to be using. RISAFloor and RISA-3D are the two programs we will be talking about. RISAFloor, if you're not familiar with that, is a building analysis tool. So in RISAFloor, you lay out your building, you lay out your floor by floor on a plan level, and carry gravity loads down the building. And that RISAFloor model will transfer right into RISA-3D. And the part of the model that goes from RISAFloor into RISA-3D is the lateral portion of that model. So for us, that will be our shear walls, our wood shear walls. And we can take that and do the analysis of the shear walls or the design of that shear walls in RISA-3D. We'll also be talking about RISA-3D on its own because really the functionality of that design is there on its own. And a lot of times during this presentation we're going to be focusing on a very micro level of a wall. So it'll be easy to just talk about that right in RISA-3D. But a lot of these philosophies that we talk about will be both for RISAFloor and RISA-3D. So definitely let me know if you have any more questions along the way about what program we're using, but we will be talking more in RISA-3D today. The versions I'm talking about here will be version 8.1 for RISA-3D and version 4.1 for RISAFloor. And it's important to note that we introduced the wood wall in RISA-3D in 8.0. So in 8.0, we started out with a wood wall with no openings, which was the first attempt of a wood wall. And then obviously we went into 8.1 with openings. But it's been an evolution of this wall, so we'll sort of see how that's affected some of the decisions we'll make in design and how things are actually laid out in the models and how we do things from when we had openings or when we did not have openings in those walls. And then RISAFloor will be corresponding 4.1. Just to note also, the current versions of the program is 8.1.3 and 4.1.3, which is just some minor patches along the distance there. Okay, so if we go beyond that, let's start out by talking about our design rules. So I'm not going to build a wall from scratch in this model, in this presentation, but we do have a tutorial that would allow you to do that wall from scratch. But we will want to talk a little bit about here will be the actual design rules that go into designing this wall. So first of all, the wall geometry is laid out in this design rule. For the first thing here, we see wood wall studs. And those studs there have, we see in the first item here, it says 2x6, two 2x6s for the top plate. The sill plate is a 2x6, and the studs are 2x6s. And in this location, you can change it to be a 2x8, a 2x10, whatever you need in there for that stud. You also can tell the program to do what stud spacing. We see here that we're using 16 inches stud spacing. We see a minimum stud spacing is 16 inches and a maximum stud spacing is 16 inches. And that right there, you can actually lay out, the program will actually design that stud spacing. But a lot of times people know what stud spacing they want. The last column there is for green lumber. So you can actually use green lumber, design parameters or design calcs for that. The next one here we've got is the design criteria for the design rules. So first we were talking about geometry. And now we're going to be talking here about the actual shear panel design. The first thing here we lay out is a schedule for that shear panel design, and we'll see that in just a second. But you can lay out in that schedule here, you can tell that on the outside of the program, on the outside of those design rules, we can say we'd like to size these shear panels to be at 5/16 starting out, or this one here we've got 3/8. ranging all the way up to 15, 30 seconds, whatever is available in that schedule. And we can help actually use these selection tools to get us basically a design that we're looking for. We can also have it tell the program to be using optimum double-sided or single-sided shear panels. We can tell the program here that we want to use what maximum nail spacing we want here. The cords that we'll be attaching these hold-downs to, we tell it as the next thing. And the last schedule we'll see is going to be the hold-down schedule. So there's two schedules. First, your schedule is going to be, that first schedule is going to be your IBC 2006 panel schedule, and then the last thing is going to be your hold-down schedule. So let's look at these schedules in particular. This is going to be our wood shear wall panel schedule. And in here, what we see is that we're looking at this actual schedule is kind of like an Excel spreadsheet. That's what it really is built off of. So it's important to see that basically we're looking at columns and rows on the right side here. And when we look at this spreadsheet, what we're doing is we're selecting the entire code. IBC 06 is what we've got listed here, so I see IBC 06, but I can narrow it down to smaller selections like a 5/16 inch panel group, or I can change it to a 3/8 inch panel group. I can change it to any of these different panel groups, and it will only select that size. We also see that I'm selecting a grouping of that, which means that the entire group or list on this we see in here in this window is going to be sized there. I can also just switch it to a single panel by unchecking that entire entire panel group. And then I will be just choosing one single panel. Okay, so are you doing design or are you doing analysis? That's going to be the difference there. So you can choose which one you want to be doing. But like I mentioned, this is all based on an Excel spreadsheet outside of the RISA program. And that was intentionally done that way. That gives you the power to customize these panel groups. So right now we just have IBC 06, but the next code comes out and the values change slightly, or you have a proprietary panel that you need to use. You can enter that information in directly outside of the program using an Excel spreadsheet. You can find that Excel spreadsheet right on your computer. It's in the C RISA folder under RISA Wood Schedules folder and then Shear Panels. And it's pretty easy. You can also find that information in the help file. Okay? The important information in here, which we call the required fields that we have listed on here, is going to be first your label. Okay? The label is pretty evident. It says the first one we can see right off the top of the list is S1 5/16 6D at 6. And what it really is meant to do is just explain what it is. So it's a structural panel, ST1. It's got a 5/16 inch thickness. It's going to be 6 penny nails, and they're spaced at 6 inches. So that's the label, and they're trying to be pretty evident about what they actually are. The next piece is going to be what's the minimum panel thickness, and that's required there because we're going to be setting the elastic stiffness of the wall during the FEM solution based on this thickness. Okay, so that's kind of a crucial design piece of information. The next one we have here is the GA value, and that's here we see in red highlighted at the end of this column. We see that's the apparent shear stiffness. Okay, and that value there is coming right from the NDS equation 4.3-1, and that's going to go right into that equation when we do the deflection calculations. Okay, the next one is going to be 1 or 2-sided. Okay, that's pretty easy too. We're going to be that was either you can set that in the design rules or you can set this up in here and choose one that 1 or 2-sided. Boundary nail spacing, again, is to help to do the optimization when we were in the design rules. Shear capacity, now that's another big value there. That's what's going to go in for the code check capacity. So what can this actual panel take for shear? What is its capacity? Okay. The rest of the fields in here are going to be optional. We're not really using them for design, and we're not really using them to actually break things down beyond for the optimization code. Okay, but they are part of what is available in the IBC tables, so we use those there and we have them available. Okay, shear capacity. So we just did mention that we have that column in there for shear capacity, and those are going to be based on seismic loads or wind load capacities. And it makes a difference. Okay, we have this actually this checkbox in the global parameters that says increased nailing capacity for wind. So if you have that checked on, then we're going to actually do that wind capacity increase for you. If you don't want to do that, which is probably not the case for most people there, you could uncheck that. But we're going to assume, and actually the program is defaulted to have that checked on for you. Okay, the important piece, though, is that you must use load categories in the basic load cases and load combinations. Okay, because how other could the program know that you're using wind loads or seismic loads, but you need to designate it in the category. So when we see here, I have a little picture showing here the dead loads, and I described it as dead loads, but I can, in the description, call it whatever I want. I can even say exactly what the load is coming from if I needed to for the description. But the category, DL is dead load, WL and EL, those are the two that I'm really worried about, but even WLX, anything with that WL as a prefix is going to now know that it's a wind load, okay? And the earthquake load is going to have an EL as its prefix. Below that, I have load combinations, and I'm going to need to make sure I call these up by category here. So you have it called out, and when you use the load combination generator, you can see that I've got my wind load listed, I have my earthquake load listed right there automatically for me. But if I do a manual load combination, again, just make sure you use those categories. Okay, so we're kind of done with those shear panels. Now let's talk about these hold downs. So again, we have some required fields in these hold-down schedules. As I mentioned before, these hold-down schedules are just the same location as we saw the shear panels. They're in your RISA folder. So if we've automatically added the Simpson hold-downs, not for any reason except that Simpson catalog is a really good and easy catalog to enter in for us. Okay, so you have somebody else that you'd be interested in adding for the hold downs, you can add that directly into an Excel spreadsheet and just drop it into that same folder, and it will be available under Select Manufacturer. Okay, so it gives you the power to do what you need to do for design. The required fields for that are going to be the label. These labels here are really straight out of the catalog, so mean really what the Simpson folks have intended us to put in there. And the next spot here we see is the deflection at peak load. Okay, that's a real important number because that number there is going to be going right into the NDS equation. So if I see here this deflection at peak load, what that is that delta A, which is total vertical elongation of the wall anchorage system, okay, including fastener slip, device elongation, rod elongation, etc., at the induced unit shear of the shear wall. Okay, so you have that number directly from the catalog, and we can drop it right into this equation. If I see the next thing here, we see that actually is described as, since this is the peak load, okay, deflection at peak load, then to find the actual deflection, it's scaled per the actual tension force. So we multiply that by the hold down ratio given in the output. And we're going to see that we're getting the actual deflection since we're not talking about peak at all times, right? So the next piece of information here on this hold down is the CD, or the duration factor. This is assumed to be the duration factor for the allowable tension value that we have. And that, if we always see here in the Simpson catalogs, they're always increasing it by 1/3. So 1.33 is going to be your Simpson catalog value that we have for the duration factor. The allowable tension here is the last column, and that's from the manufacturer's catalog as well. It's adjusted based on the difference between the assumed and the actual load durations factor. So, for example, you're going to be getting here a 1/3 increase for this duration factor for this, but this may not be the load combination that you run. So for your load combination that you run, you need to actually adjust that to get your true allowable tension. All the other fields are optional, okay? So again, we put them in there for your information because they are part of the actual catalog information, but we don't really use those in the design portion. We're really just using those design features that I've told you just right here. Okay, so the next thing let's talk about is boundary conditions. So we've kind of laid out what the wall itself is going to be like with its design properties. We've talked about its geometry. And now let's talk about what happens with the boundary condition assumptions. By default, I'm looking at a wall here on the left side. By default, we assume it's continuously pinned. And what I mean by default means that if you just draw a wall into RISA, and you don't address its boundary conditions at all, and you just solve the model. Well, unlike a beam or a column where you have to go in and tell it the boundary conditions, we're going to actually make an assumption for you. Just say, okay, that wall is pinned at the base. And not only is it pinned, but it's continuously pinned. So we can see from my picture here that that means that at each internal location of a plate intersection, I actually have a pin. So we're seeing a little bit of a force on this one here, in this simple wall we looked at. Now, the reason why I bring this up is because when you do a manual calculation or you set something, when you do a hand calc, you're looking at a wall, you typically look at each side of the wall, okay? So you see that you think about things from each corner of that wall. Especially if we're talking about lateral forces, okay, that you would do maybe talk about the tension side and the compression side of that wall. Well, if you want to do that in RISA-3D, that's an option for sure, but you will want to make sure that you set the boundary condition to free. And there is an availability to put that in right inside of the wall panel editor. You can tell the program to do free as a boundary condition, and it will turn green. Okay, you can see from my picture it turns green, and then you get those. You'll actually get hold downs in place on each side of the boundary condition when you run the model, and each hold down will act as if it's just a single pin on each side. Okay, but what's important to note beyond all here is that all boundary conditions need to be defined inside of the wall panel editor, okay, not on the external boundary condition spreadsheets or graphically outside on the program. If you do things outside, they're going to actually interfere with the wall panel editor, okay, and the wall panel result. So that's definitely something that you do not want to do. When we talk about the wall panel boundary conditions and looking at the results, we can look at the joint reaction spreadsheet, and in there we can see that we have the wall panel 1 here listed. It gives me one load here, one force for the x direction, the y direction, and the z direction, as well as moments in the y and the x and the z. Okay, and you get one number. Basically, we're summating what's happening along that distance there. Okay, so you can see maybe on this wall here, we just get a summation of forces in the x and the y and then a little bit of mz. Okay, that's going to be for that wall. But you can also show it just like I'm showing it on this page here, display it individually based on the individual plate forces. So when we're looking at here, we can turn on, in the plot options, we can turn on our display joint reactions. And then we can actually see how each plate model is showing, each plate intersection is showing that there. So I'm going to take a second here. I'm going to jump into RISA for a second. And let's take a look at this model that I built. Okay, this is actually the model we were just looking at in PowerPoint. And what we've got here, I'm going to run this model, but it really is just the simple model we looked at, dead live load and wind load. Okay, we've got some load combinations. And first of all, I just really want to show dead and live load. Okay, so if I solve just the dead and live load, so just vertical loads, what's important to note about why maybe you would run something one way versus the other is to kind of display what happens. Let's turn on the deflected shape. So if I come into the deflected diagram and I turn on the load combination, I'm going to amplify this by maybe 200% and just sort of see what happens in this model. So one of the reasons why we would want it to be continuously bound at the bottom is sort of this picture and how well it demonstrates that. First of all, it's unlikely that you will have sort of an elevated boundary condition that allows such a deflection to happen underneath the sill plate of your model or your wall. Okay, so that's sort of an odd thing that we're seeing, that we freed the one side here just so it would match our hand calculations, which it does nicely match our hand calculation, but that's not quite what happens in reality. Okay, more in reality, you've got sort of a boundary condition at the bottom. The entire thing is supported, and then it actually is distributed by those supports there. So like I mentioned, you can turn those things on by just going to your joint reactions, and you can turn on your X, Y, and Z, and we don't have much moment here to look at, but I will turn that on for us too. And we can see how these boundary conditions actually are displayed on the screen if we could zoom in a little bit closer. Okay, so what's nice is that you do match your hand calcs, but not quite really accurate. And one of the biggest pieces that actually sort of not only does that really bother me underneath the wall, but on top of the wall, you can see that our deflection is just so different from one boundary condition assumption to the next. If we just look at N2, for example, that one joint on each wall, I'm going to unselect that. I'm going to just check N2 and N6. And I can push this exclude button, and that will exclude all the results except giving me just those two results for those two joints. And I can see the joint reactions here, and I can see how much different the deflection in the y direction is. And this is just gravity loads that we're looking at. Okay, so not too much load on this wall, but it's a lot different in its deflection. So not kind of hard to justify that. So what we'll want to do is we'll want to go. Let's jump back into our PowerPoint and talk about that for a second. Okay. So let's talk here. So we kind of understand a little bit more about that boundary condition and why we would want to do it that way. So now let's talk about this finite element analysis. So I didn't really show it just now, but it's really important to note here that what's behind all of these wall panels is really a plate model, okay? It's automatically meshed. The plates are seen here. What you can see, I dropped in a opening into this wall panel here that we're looking at, and I can see that it's just meshing right around that opening. And that's all happening behind the scenes for us. So we don't actually affect any of that plate model, but we can control some things on that plate model. First of all, we can show the plate model, okay, and that's an important thing so you can see how it works. One of the biggest things I think RISA is great at is just displaying things so that you have a real good understanding of how things are working in the model. So understanding your mesh is by seeing it. So let's turn it on. You go to the plot options, and then under the panels option there's a show mesh box, and you can turn that on, and that gives you this nice picture here. But of course, not something you always want to see. It would be a little bit over graphic to see it at all times, but we could turn that on. The other thing we might want to do here is affect the mesh size. So in the global parameters, you can actually affect that mesh size. Right now, what's affecting my mesh size is really that opening is sort of going to that to help develop that mesh. But it doesn't need to be so fine maybe. Maybe it could be a little bit more coarse in its mesh and still get very accurate results. Okay, so right now, our program defaults here to 12 inches mesh size, which means that it goes to a minimum of 12 inches there, and then it will actually size below that. So that's actually, a maximum of 12-inch mesh size. Okay, so if I wanted to make these mesh larger, I would just set it to maybe 24 inches, something like that. Especially in a big model, you might start to say, hey, that mesh size needs to be adjusted. But one of the things, when I say automatically mesh, it's also very important to note that if not only openings will it mesh to, it'll mesh to joint locations. So if I drop in some joints in here for loading, or if I have a line constraint, maybe I have a diaphragm cutting across somewhere. Not typical that you'll run a wall up over a diaphragm, but maybe you're doing some balloon framing and you actually have a diaphragm tying in somewhere along that height of that wall. That will actually mesh to it. Okay, so it's a real good tool that all of these things are meshing automatically behind the scenes for you. Let's talk about loading here, since I did open up that can of worms. One of the things you can do is you can do wall panel loads here, distributed loads. Okay, that's one of the most common ways to load a single wall, and you can do that in the local axis or the global axis. Okay, you can actually do any direction you want on those distributed loads. You can also do joint loads. Like I mentioned, you can joint load anywhere on the wall, and the mesh will fit to it. So if you put one in the middle of the wall, for example, it will actually mesh to that properly. The only issue with the joint loads is you just need to create a joint first. Okay, not too hard, either through the joint coordinates spreadsheet, or sometimes I just start a beam to create a joint there. So I've got that. You can also do surface loads. And surface loads are allowed on any type of wall. I wrote here not advisable for wood walls, but that's actually very important to mention that it's probably flexible diaphragms that it's not real great for. One of the things we're doing here is we're not doing a whole lot of out-of-plane stiffness on that wall. We have some out-of-plane stiffness. We try to calculate here what the out-of-plane stiffness would be for a wall panel, but it's not as much as it would be when you're in plane. So distributing loads out of plane, like for example, if I was just sort of blanketing wind load on that, it may sort of actually push it out of plane too much with a flexible diaphragm. Maybe with a rigid diaphragm it would help us distribute the loads a little bit, but with a flexible diaphragm there's actually no real diaphragm behind the scenes, it's just a distribution of loads. So we'll talk more about diaphragms a little bit later, but the issue of surface loads, it can be done, but definitely you want to be wary and take a look at the results and make sure you're not pushing that wall over and not having enough stiffness there, okay, because there's very little out-of-plane stiffness, as I mentioned, compared to in-plane stiffness. Okay, so let's jump into some design information. So when we run the model here, when we run walls, in particular we have 3 different types of walls that we can do. We can do segmented, perforated, or force transfer around openings. And we'll start with segmented. Okay, this is actually where RISA began, with a segmented wall without openings. So we'll talk about segmented to start. And the way we talk about segmented is it's based on regions. So, and those regions must be defined within the wall to have a segmented design. So when I look at the right here, I can see I have 3 regions, region 1, region 2, and region 3. And those regions there are defined, and another word for regions maybe is pier design, things like that. But it's pretty, a region is sort of an area, a rectangular area, which is important to make note, that it has to be rectangular, and it can actually be, you can define it anywhere. You can actually put regions any locations, but they have to be rectangular. The regions can be defined by the user. There's inside of the wall panel editor, there's a little button that will allow you to define your own regions. You can push the little button that will auto-define them for you, which is right here. Looks like a little A on the same kind of icon. Or you can just not define them, okay, and let the program define them for you at runtime. There's sort of benefits to each different one. The program originally didn't have the smarts to do this auto-defined regioning for you, so you always kind of had to do it yourself. But as we got a little smarter here, we figured out how to do that. But there are times when you're going to want to take control of your region and where it's located. So you may want to, we sort of left that tool there so you can always go back to that. And then there's times when you just say, I just want to run the model and see how it goes. So it'll actually do that for you at runtime. So you have some options, and that's kind of a nice thing that you can maneuver. And then in segmented, in particular, only full height regions are designed. So region 2, for example, is not a full height region. That is a region over an opening. Okay, so above and below openings, those regions are not defined. Okay, the code actually sort of NDS code sort of leaves that out as a region that will not resist the lateral load. So we are not designing that. We're designing R1 and R3. Okay, and then the hold downs are automatically placed on each side of the region, and this is for segmented that you'll see now here. There's just going to be a hold down that pops on the bottom of each side of these regions. Okay, so let's talk a little bit more. So we talked in here, we said that you can do segmented, perforated, or force transfer and openings. And we see that in here, right in here under segmented, perforated, and force transfer. It's just a drop-down list. What's nice about that drop-down list is you can switch it between the different ones and see how the wall behaves. So do you want to do segmented, maybe start out at segmented and you try the other ones to see. And maybe you learn about how the other ones behave on your model a little differently. Okay. The other thing is if you wanted to, you can just jump right into the wall panel spreadsheet and change it right there. So you don't have to be in the wall panel editor. If you know all of them are needing to be perforated, you can just highlight the entire row and change them all to be perforated. Okay, so you have a couple options there to get in there. For segmented design, we've got here, we can look at each wall has its region, as we mentioned, and each region has a chord defined on each side. Okay, so each region is going to be designed separately, okay, and we're going to see here a detail report for each region that we're looking at, and so they're basically like separate shear walls on each side of the opening, okay, and as we mentioned earlier here, above and below an opening are not going to be designed, and they actually are ineffective sections, so they sort of drop down their shear levels there just so they really can't resist a lot of shear, but we just sort of transmit the forces from one region to the next that is actually an active region. And as I mentioned, there's going to be hold downs placed down at each side of each region because it is a separate shear wall kind of identity there. Let's jump in and take a quick look at a shear wall in this segmented design. So I'm going to open up a model called, and I have all these models available for you. Hold on here. I'm going to not save the changes, and I'm going to open up segmented wall design. So at the end of the presentation, feel free, we're going to post all of these models here on our website, so you'll have that available, and you can kind of play around with the models that I've been discussing, and then also look at here, as I mentioned, the PowerPoint, so you can kind of follow along. Okay, so this is a segmented wall, and if I can just double check that by double clicking on it, and I see here I picked a segmented wall. I see the different regions. This looks very similar to the one I have on my PowerPoint, if not exactly. And I can double click on this one here, and I can look at that segmented there. And what I can do is I'm going to run this model. So I'm going to just open up a load combination and maybe just run the batch. So I'll run through all the different load combinations available, all 18. And I get a big warning message. And this warning message is really interesting here. And what we're doing is it tells here the shear panel 2, which is my second wall here, at 20.5 feet to 22.5 feet does not satisfy the height to width ratio. Design was skipped for that shear panel. Okay, so what's happening is we're enforcing a lot of the rules that they have in the NDS on the shear aspect ratios. And that aspect ratio right there in the middle of this wall is not being met. And so first thing you'll notice is that there's no graphics on it. Okay, so region 1 and region 7 in this wall actually show me some graphics of what was designed for the hold down, what was the cords, what was the actual studs, and R4 has nothing in there. Another thing that you'll note here is I'm going to just click on my detail report for a second and click on that member here. And what I see in here is that this is a detail report, pretty evident of what we have, and we'll kind of go into this a little bit closer. But R4 in particular is not being designed, okay? So I have NCs everywhere, and then when I look at my region report, I get a list here of the regions that are in there, and region 4 just tells me it's not being designed. So it's a nice little warning message telling you a little bit further about what happened on that wall. And then you can kind of investigate, hey, maybe I really don't care about that region, or maybe I do, and I need to worry about, I need the contribution of that panel in there, and I need to figure out my openings differently. Okay, so let's jump in back into my PowerPoint here for a second and talk about here the header design. So header design is not being designed inside of a segmented wall, and the reason being is that on top of that opening is an ineffective section. So because that's ineffective, it'd be hard for us to actually do a header design there because there is no real shear loads, and the loads are being kind of actually moved to the side of that ineffective section. So we really don't have a load path to get into that header for this for a segmented design. So if you do want to do your header design, you want to switch over to perforated or force transfer around openings. Okay. And again here, the height to width ratio is required for the NDS. So, and we just saw that, how that was demonstrated in the program, giving you a nice warning message and alerting you to that fact when you break the rule. Okay, so let's take a closer look at this segmented detail report. It's pretty obvious to look at, but there's a lot of stuff hidden in this, and I want to make sure that you see everything and how things have changed. These detail reports have evolved. We have, I feel like, have come to a really great wall panel detail report that has all the information you possibly need, and then you get to go into even the details beyond that in the region report. But this is a great one-page summation of what's happening, just very similar to our beam detail report. So first of all, we echo the input. So when I can see here, we've got the input from that wall. As I see the NDS 2005 segmented design. I see that I'm using 2x6s, Douglas fir. Okay, pretty obvious stuff from my actual design rules. Then I see the geometry of that, the total height and the total length. And what's important on this piece of little information here is the maximum height to width ratio. Okay, so that right there is 3.33, and that's per region, not per wall, which is important for a segmented design, right? So I've got 3.33, which is not 10 divided by 10, but it's probably here R3's dimension by its height, 10 feet, okay? So we can see a little farther in the regions when we look at that what the actual geometry of it is. The envelope results displays here the controlling region, which was R3. Okay, R3's got here, it tells us the shear panel that was selected, the unity check, the load combination that contributed to that, which is 10. The load combination actually also distributes the wind, whether it's wind or seismic. We see a little W in parentheses everywhere here. Well, that's because the wind and the seismic, we're going to see a little bit of increase factors happening there. So we want to make sure we know which one did it. Was it seismic or was it wind? How do we go back into that calculation? Okay, we've got the hold down information, hold down locations here. We can see that we've got the hold down, load combinations, and then we also see stud design and the combination that yielded the worst ratio for that. And UC is unity check, just like we do have for beams. We'll see UC for unity check and LC is load combinations. Okay, region reports breaks it down on a region level. Again, very important for segmented design to understand what's happening in each region. So we get it broken down very, very similar to what we're seeing above here, but on each region we see a little different information. Okay, and lastly is the deflection results. We're going to talk here about deflection results, and what we see here is that we have kind of deflection results on this page described sort of a little differently than we might expect. The first thing is that it gives us the maximum region deflection, and that's based on the NDS equations. So we're getting that three-part equation, and we're seeing that right now is 0.6 inches there for region 3, and the load combination 10 yielded that. Now, the finite element deflection is going to be different. Why are those two numbers different? So what's happening is that the maximum region deflection is going to be based on, let's see, do I have here? Okay, let's take a look here. This is the equation that we're going to be governing, the NDS Special Design Provisions for Wind and Seismic, equation 4.3-1. It's a three-part equation, and that's our first component that we see in that when we were looking at our detail report. What it does is this equation breaks it down for us here. The first part of it is going to be the flexural component of it, and that flexural component of this equation is based on the chords. The E and the A, so the E and the A, the stiffness and the area here of the chord is actually the first component. Okay, so once you tell the program what chords you're using, this part it actually is calculated. The next piece is going to be based on the apparent shear stiffness, or the GA value, okay, and that's the shear component. And that's going to be calculated here in combination with the minimum thickness, panel thickness that we set when we were in the schedule to set the elastic stiffness of the wall. So we see the shear component, we see the flexural component, and then we also now see a elongation, or a hold-down elongation portion. And that's coming right out of the hold-down database that we had in the beginning here. So it talks about the total vertical elongation of the wall anchorage. Remember we talked about it being a fastener slip, device elongation. So all those pieces of information go into this one delta A, and then we plug that into this equation. And then you get a total deflection value listed here, and the governing load combination that yielded that, because there's little v here for all the shear values that we're using. So that's your basic NDS equation value, and that's so that's an equation. You're just plugging and playing on that equation. Now we also have a different number in here. It's called the finite element deflection, and that's going to be based on the stiffness of that wall. So we don't have that stiffness is going to be something that's basically how thick is that plate, and what is the stiffness value in the shear level and the shear direction in plane direction of that plate. So those two values won't always match up. and probably rarely will. You'll probably have to sort of tweak that. And what we're trying to do is get those FEM results, or the FEM deflection, to match that hand equation that we've got there. Okay, but you're looking at a computer model versus a hand calc. So you're two different theories, and what we've given you here is this value called the shear stiffness adjustment factor. It's sort of what we see here is right now it's defaulted to 1. We call it the SSAF. A lot of places you'll see that as SSAF. And what that column lets you do is, I always like to think of it as sort of a dial. It lets you dial in how the finite element model behaves according to how the NDS three-part equation looks. Okay, so getting those two numbers to match is the goal here for you to sort of get that. And also the question is, how close should they match? There's going to be kind of a question of maybe they will never get to be identical, but they'll be close and adequate. And if they're not, we can actually describe at the end of this conversation here. We'll talk about why they may differ even and still differ. So we've got a little bit of a way to turn this dial, and it's really going to be either up or down. Do you want to make the shear stiffness higher? Do you want to make it more stiff or less? And you can adjust that. So with this adjustment factor here, the user can match up the deflection from their hand calcs with the FEM joint deflections at the top nodes of the wall. Those are the two nodes we're looking at when we look at these two numbers. Okay. So we've got all that information here listed, and this is going to be our wall detail report. The next piece of here, let's take a closer look at this segmented design by looking at the controlling region. So if we jump right into this controlling region, we see that R3 was the controlling region, okay? And if we jump right into that, we can see that we've got the region detail report. In this region detail report, it's just a drop-down list here. We pick out region 3. We can see a lot of the same information from the echo input. We told the program that we were going to be using the 2x6s, right? We saw that information before. We can also now see here the geometry a little bit better. Well, first of all, that height to width ratio tells us a little bit more about what that height to width ratio was. The capacity adjustment factor, that's an important number. Okay, that's actually right from the NDS. It's from the 4.3.4.1. Okay, long numbers here, but really what it does is it tells you somewhere in there that you can multiply it by 2bs over h. Okay, in the program we say 2w over h, and that is a capacity adjustment that allows you to adjust that there for your shear. We also tell you here if you're going to be allowing a 40% increase of tabular values for your wind, if you're going to be using wind, and that's right off that global parameters. Remember, we saw that a little bit earlier. And then we tell you, again, what the stud spacing was. So what was it finally selected, or if it was actually designed by the program. So we've got all that in the geometry. And then here we see the first kind of design information. So based on the design information for that shear panel, what is the required capacity? So we've got here what's required, what's provided, and what was the ratio, okay? Again, that shear capacity is coming right out of that spreadsheet that we saw earlier, right from the design rules and the schedule, and that's based on the IBC, okay, tables. We have our chord forces. So we see maximum compressive forces, we see compressive capacity, we see the ratio of that. Then we also see tension forces and the ratio of that. And we're seeing different load combinations for tension and compression. And it's important to note how we're calculating these chord forces. So chord forces here, we can see a picture. If we apply a shear load to a wall, we're going to see chord force. So the chord is going to be on either side of that, okay? And you've got a chord force of a compression on one side and tension on the other. As we see here, we can calculate these values a little bit differently. For the tension side, per the NDS 2005, there's a little segment in here, 4.3.6.4.2, that tells us to include the dead load stabilizing moment for when you're using the tension forces. But for the compression forces, they say don't use that dead load stabilizing moment, but use just a tributary area of one stud spacing. Okay, so we've got, if we look at this in a calculation type format, what we can see is that for the chord force, we're using the moment times divided by the length to find that in tension. Okay, and then we see here that we're actually subtracting out the force here, the P, which is the axial force, over 2 for the tension. Now, for compression, we're not taking that full P over 2. We're taking just the P of 1 divided by 1 stud's dimension there. So if we're 16 inches on center, we're just taking that little portion of that into play for the compression there. Okay, so we've got those 2 different methods for calculating the compression versus the tension side. And then we're really talking about this is per region when we're in segmented design. So each region is going to have this different chord force on each side of each region. When we're in force transfer around openings or perforated, what we're going to see is that it's going to be the entire wall behaves this way based on this shear force, and then we get chords on either side. Okay, we don't break up little chords inside of a FTAO or perforated wall. Okay, so stud design also, let's talk about stud design. Stud design is based on the enveloping of the maximum section forces from each region over the entire wall. Okay, so what does that mean? When we run the batch solution here, when I just ran the batch solution or the enveloped solution, either one, what we're doing is we're taking all of the load combinations and designing for that. Okay, so when we think about that here, stud spacing is required. It shows us the required capacity, and then it shows us here the design rules explicit here. Unless you have explicitly told it what you want, we're going to actually design that based on what's required. The other piece is that we're going to give you a code check, and that code check is just what's provided and what's required, and you get a little code check showing that. When we optimize that wall, what you're going to see is that we're going to just bump it by 2 inches. So if we said, okay, go anywhere from 16 to 24, we're going to try 16. We'll start at the other side. We'll start at 24. We're going to go to 22. We're going to go to 20, and just bumping it down by 2 inches to see what works. Okay, but I noted that we're enveloping all of the entire load combinations are going to be considered. When you're running a stud design, you probably only want your gravity loads in there. So you may just want to select a batch solution with just gravity loads if you're designing your studs. Otherwise, you're going to be actually taking some of that. You're not actually taking it out of the wall for your lateral design, but typically people want their lateral design to go just to their chords, and they don't worry about the studs for lateral. So maybe you do. So you just want to know how it's behaving. But that's definitely a question to ask yourself. Should I be running the entire load combinations for the gravity of the stud design there, or excuse me, for the design of the stud, or should I just be doing gravity? And I think I would suggest gravity only. Hold downs is the next spot, and I want to talk about the hold downs here. So in hold downs, what we see is required capacity, and this is only going to be the tension forces. Hold downs are not going to be needed if you don't have tension. So we're always seeing that. So kind of directionally, you're always looking at a tension force there. Provided capacity is allowable tension, and this is right from your hold down database, like we saw. You've got the hold down governing, which is the largest tension force. So we might not see here the same values here, but we should see tension capacity for our chords, and we should see the same load combination up there. Okay, but note when you're looking at your deflection calculations, that's going to be based on the maximum shear force. So you may not get the hold down elongation. That's going to be from a different combination. This is from 10, which governed here for the actual, is a lot larger in compression than we had in tension. So that's our deflection calculation. Okay, so selected shear panels. Once we've got a design here, once we found the model, found the shear panel, we found the hold down we're going to be using. What we see here in the detail report, we see the echo of all the information again. But we also see that we are now applying. So just the shear capacity right there is listed from the database, but we also adjust that based on the capacity we saw here, 2BS over H. Okay, that's that equation here we were talking about where you can adjust it based on the seismic. You can also adjust it based on the wind force. So you can see a 1.4 increase for the wind. So which one are you actually designing this for? Which governed will tell us here how it got adjusted. This one's a wind one. 1.4 is actually adjusting it there. Once we have our shear panel adjusted, we're also going to do our hold down information. Again, it just echoes out the information of the hold down that was selected. And then what we see here is we do a base capacity. So we take the capacity of that from the manufacturer, and then we get the actual capacity based on the base capacity versus the times the duration factor. And we see the duration factor was a wind, so it was 1.6, and that's how we get our base capacity, our actual capacity here. Below all that information on the detail report, you see the cross-section detail, and that just shows us a graphic picture of what's happening in this. So we see the wall thickness, the stud spacing, we see the sheathing and panel designation listed out for us. We see the chord sizes and forces. Now, the thing to note in here is we see a little C in parentheses. That means the compression is actually governing for these chord forces. The hold down designation and forces we see here, and we see the load combination in parentheses for that as well. So you're going to be able to see all the different pieces that went into, and if you have sort of questions about that, now you can just go ahead and run load combination 17 by itself and really see how that behaves and investigate things farther. If either chord is experiencing compression only, the hold down force will not be displayed. Okay, so since if you have compression, you won't need actually a hold down, so you won't have it displayed there. Okay, jumping ahead into perforated design. So we really covered all of segmented design, and now if we talk about perforated design here, we can look a little bit closer on the perforated design. Perforated design is going to be using only the portions of the wall that have full height sheathing. Okay, so L1 in this picture is going to be used for our shear wall, and L2, LO here, these are going to be the opening sizes, and they're not going to be used in the design. So it really treats the wall instead as a significantly shorter wall. We really kind of just collapse this wall into a very short wall, subtracting out all the areas that are above and below openings, and that whole entire region gets kind of not used. But what that also does, it amplifies the chord and hold down design forces significantly, while at the same time increasing the design unit shear. Okay, so there's pluses and minuses to all the different methods, but sort of so you see how it behaves. There's a number of constraints, and that's one of the other things about perforated is that there's a long list of reasons, things that you have to follow in order to use the perforated method. RISA is enforcing all of those things. So if you break some rules, just like we saw for the when we broke the rules of the aspect ratio, you can break the rules. One of the rules there is it can't be higher than 20 feet. Okay, so if you try to build a 22-foot wall with a perforated design, it's not going to allow you. It's going to give you a warning message, which is really helpful so you know that you just went outside of the code. Okay. Now, hold downs, like I mentioned, are only going to be required at the end of the wall, okay, for perforated, and for force transfer around openings, the same kind of rule. Okay, so we'll see hold downs only on the exterior of the walls. As I mentioned, too, you can get perforated design. You're going to be able to do your header design in here. So we can see here in the header design information, this is from the detail report. I can open it up here in just a second. We can take a quick look. But I want to make sure we talk a little bit here. So all load combinations are enveloped just like we saw when we were doing stud design. When you run the load combinations with a batch, you're going to see that they go right into the header. Do you want to run your header design for shear loads? That's a question you may want to ask yourself. I would suggest probably just running it for gravity loads. So again, batching a solution for just gravity loads in order to get a shear and moment diagram that looks similar to this. I can show you what it looks like if we run all the load combinations here, and we'll see that in a second. But I think this is a pretty good suggestion of what you'd want to do. Also, you see here that the code check is based on the shear and moment only, not on the axial loads. Okay, so from kind of experience, we saw that really it's axial loads are not something that you're going to be designing your header for. So you end up, we took that out there. So you're just getting those shear and moment diagrams. Okay, so let's take a quick look. I'm going to open up a perforated model. Open this up. I'm going to say, let's see, perforated wall design. And if we just saw this wall, this is just perforated, not any different. And what I can do is I'm going to open up wall. Let's take a look at this wall. So if we look at this wall here, we see, we'll talk a little bit closer about the detail report and the information again in here. But right now you'll notice we don't have a region drop down. We only have openings and walls. And if I go to the opening report here, I can see here that this is basically very similar to what we just saw in my PowerPoint, which is giving us a description of the shear moment diagram with the code check information, okay, just below, just like a typical wood beam code check information, okay. But what I can do is I can run the load combinations here. Let's run the batch solution. So if we run the batch solution, it goes through all the different load combinations, including the wind load combinations that were applied to this. Let's double check if we have some in here. So we see wind loads, we see dead loads, and live loads in this model. And then let's take a quick look at the header design. Okay, so if we look at this one and we go to our opening, we see a lot different shear moment diagram, because what we're doing is we're dragging our shear loads through that actual element there, through that header. So we're going to see some odd behavior in that shear moment diagram. It's not odd if you think about what's happening, but that's why I really do suggest that maybe this isn't the way you want to design your header. Maybe it is, but what I'd say is you probably come back in here in your load combination and you say, let's say, I'm going to say turn off all of these loads and just come back in and say just run the dead and the live loads. And maybe if I have roof and snow loads in here, okay, and I can run those. And I'll run a batch of those solutions together, and now take a quick look at the opening, okay, and it looks a little bit more like we would expect, okay, and that would be where I would recommend you being. So that's where my openings kind of go from. But let's take a closer look at actually the detail reports. So we've got, for when we mentioned here, what we've got is for perforated is we're doing a summation of the L1, L2, all of the full height regions. We're summating that. Okay, so then what we want to do is we want to actually take that and find our maximum shear force. So we're going to take the total shear and divide it out by our summation of L's and our CO, or C naught. And C naught is something that's going to be actually calculated here in a second. But let's talk about also that there's a different equation here for your tension and compression forces. It's not really like what we saw for the segmented design. This is actually going to come in and you're going to say the shear times the height divided by the C naught over the length, over the summation of the length, and you get tension and compression forces right there. Okay, and that's right out of the code. So pretty easy to sort of back check that. But the C naught is a number that you kind of want to go back in and also adjust. C naught is actually coming right from a table that we have in the NDS. It's 4.3.3.4. However, the problem with that table is that it is a table, and you can run off that table. It's giving you wall heights of 8 foot and 10 foot. Well, we don't just let you do 8 and 10, right? We let you sort of build whatever wall type you need. So what we did is we kind of researched this, and we went into the NDS 08 and find some calculations here, some actual equations to help us guide to find that C naught outside of those regions. So we've got those equations listed here, and let's just sort of run through this so we understand how this is running. When we look at the detail report, what we see is that we are going to get a lot of information listed out a little bit differently. First of all, the AO, okay, which is the area of the opening, is a big value when we're going into these equations. And that's defined as the maximum opening height shall be taken as the maximum opening clear height in a perforated shear wall. So I just want to make note of that, because when you have an opening in a perforated wall, you're actually going to get a different C naught if it's a window versus if it's a door. It's the same exact wall, okay? So you can see that if I look at this one here, we're going to see this A naught in my wall right here is 2.5 feet times 5, gives me 15 feet, and your A naught's listed right there for you. And then if I go to the next value here, my R, right off this equation here, to solve for that R, I use this A naught and the height, okay? And then I get my R of 0.83, which is listed below there. And the next one here, I can see my C naught comes out, and that's actually based on the R and basically the R. So we just solved for that R. So that's really all, and the height and the geometry of that information there. But otherwise, really, you come out with these different values, and you're listed out, and it's going to adjust my shear capacity by 0.83. Okay, so I've got that for a door opening. Now if I click on the next one here, and this was actually with a window opening, I do the same equation here, listing out all the different things, and for this window opening, I get a C naught of 0.99. Okay, so you're actually getting different values based on that. Really what comes down to is that R and C naught calculation are going to be slightly different based on that if you're having a window or a door opening. Okay, and this all can be found right in your detail report. So you need to make sure you understand those values there. Also here, we look at perforated and shear and force transfer around openings design. When we look closer at these here, we can see we're going to be looking at the same type of information we saw previously in segmented, but this one we list out a little bit differently. It tells us the chord forces, and it lists out maximum compressive, maximum tensile forces, and the load combination that governed. You just see it kind of in a different layout. Again, it'll show us in picture format in the actual drawing of the cross-section. The studs are also listed in here, showing us capacity versus required and provided. We see here the next one is the hold downs listed, and this again is for only tension values, so we're seeing hold downs listed there with the actual governing load combination. So basically that's your perforated design. So I would encourage you to take a look a little bit farther in the perforated and test it out. I do have that model that I worked with too, and you can pull that one down to see how the two different calculations. For force transfer on openings, this is a little bit of a different method, but we're going to kind of see a little similar to perforated. But what we do is we do a rational analysis of the wall, assuming that the straps and the blocking can be added at the corners of the openings to transfer the sheathing forces across these joints. So this picture here really shows us how this, this picture shows us how this actually operates. The wall is broken into blocks, and so we see 1, 2, 3, 4, 5, 6, 7, 8, and these blocks are really just sort of regions again. You don't need to draw regions. I hate to use that word because I don't want to confuse you by regions, but these are blocks of area, and the plate elements are sort of are basically behind these block elements. Okay, the sheathing is assumed to resist the shear forces. This is essentially allows you to use the entire wall minus the opening to resist the shear wall. So it's a little different when we saw segmented. Segmented had an ineffective region, so 4 and 8 were not being used. And then perforated, we saw those sort of dropped out of the area as well. We were just using 1, 2, and 3 and 5, 6, and 7 when we were in perforated. Okay, so this allows us to use a lot more of the actual area of the wall. And as I mentioned here, RISA breaks these into blocks. So we're going to see these little blocks, and we're going to reference always these block numbers. This is only valid for window openings, not for doors. We actually are taking advantage of 8 and 4, so we need basically to have those regions in there to have have window openings, not doors. If you dropped it down to a door opening, the program's going to give you a warning message and say has to be a segmented or has to be a perforated. Okay, so when we go into what we find is it's going to be the header detail report that gives us all the information for perforated, for force transfer around opening. So when you look at previously we've been looking at the wall detail report or the region detail reports. Now we're going to be looking at the header detail report. And here what we're going to see is that we see the average force in each block is going to be displayed in each location. So we see this here, this block number, and it shows us unit shear, okay, listed out. And then it tells us here the average unit shear per region. So for example, on this one wall here, we can see that block 1 is giving us, which is at the bottom left corner, giving us an average shear force of 217 pounds per foot in that area, in that block, okay? And the height to width ratio is 0.625. The maximum for this wall happens to be at 6, okay, which is right on this side here, and that's going to giving us 438 pounds per running foot as for the average unit shear. Okay, that's this portion right there. So what we are going to do, we also can even confirm that by looking closer at this wall. We can just zoom in and take a look at what we've got. And what we have in here is a contoured map of this wall. And the area weighted average is basically the FXY forces are used to determine the average shear block. So in order to kind of justify these average forces you have that are displayed in the header results, you may want to turn on your contours. Again, going into your plot options, you can say, okay, let me look at my contours, turn the FXY on, and then what we do is we're just looking at the average across this area. Okay, so what it'll do is it sort of gives us a guide here of what's happening in this area, which is an average of what happened for this entire block. And that'll help you sort of understand how these values came to be. Not only do we do that for the actual header, we're going to give you some information here also, for the straps. We give you the forces for the unit shear in each block, but we also want to talk about the straps that are required. Okay, strap forces are now shown on the block. So what we see here is that also we have the name of the strap. Okay, which actually this picture doesn't have the name of the strap on it, but we S1, S2, S3, all the way through 8. Then we see what the location was, so that is actually a little bit better to help describe here. It says bottom left and which direction. So that would mean here this S1 would be here, and then it would be the horizontal direction. And this is the required capacity for this load combination that was run. Okay, we get all that information in the header detail report again. And what we're doing is the moment at each block, above or below the opening, is being transmitted across the opening interface by horizontal straps or compression blocks. So above and below the opening here, we see that we're actually assuming that we're doing this transfer of load across this interface using either tension or compression blocks, tension straps or compression blocks. That's the assumption here, okay? And if you see in the next one here, we talk about the moment at the edge of the left and the right side of the openings are being transmitted by compression and tension straps. But, however, it is likely that the sheathing and the king studs are capable of transmitting these studs. So we don't actually, I don't have a drawing showing this description how this is transmitted. But what we assume is that you have those, that we give you those forces there if you need to design for them. Okay, so you've got all the strap information to be able to put the strap forces right in there. And this is kind of the most finite element analysis type of tool that we have for walls. What we're doing is we're plating all behind here and getting these unit shears and then giving you these forces by cutting, just basically using our line tool, our internal line summation tool internally, obviously, to get these forces cut across these different intersection points. Okay, so when you look at the results, it's going to be force transfer around openings and perforated results are very similar in the result layout. That's what I mean by this, not in that you're going to get identical results, but that your layout is very similar. So you can always sort of refer to your force transfer around openings and your perforated results as they are very similar. But what we do here, again, we echo the input right into the on top of here, and we see what design method we used, which was force transfer around openings. We see that we are adjusting just similarly. We are adjusting the shear stiffness adjustment factor. We're using the SSAF, that is, and then also we're using a capacity adjustment factor like we mentioned previously in perforated, 2W/H. Okay, that value right there is actually adjusting the shear capacity right directly below here. So you can see that we adjusted that. It's not adjusted in this example, okay, it's 1.0, but if it was, you would see an adjusted capacity down below there. Okay, you get your wall deflections. Again, these are based on the equation, NDS equation, 4.3-1, and with the total of the three-part equation. And then we get our wall results, okay? Now, what you'll note is that in this wall results, this total shear here, okay, is the total shear across, typically the bottom here is the maximum total shear. But the max unit shear, that 438.77, was right out of that header report, okay? Remember, we just saw that was the maximum unit shear, okay? That was for region 6 that we saw over here on the right. So that's what's coming right into play for this. And we see shear ratio, what we found for the actual total versus the provided. Okay, so you've got, and that was 459 provided here, and then total capacity needed was here, 438. So we've got those numbers in there, but they're based off of the header report. So you want to come, if you needed to verify this number, you'd go back into the header report to see that. Okay, force transfer around openings is basically, we're finished talking about that. But I also want to talk about how you can kind of do some straps and different things with stacking walls. You can stack walls on top of each other using straps. So we've been looking at walls, and I'm just going to flip back here, and you can see with these hold downs as a little logo, little icon at the bottom of each side of the wall. Again, force transfer around openings just does it on either side of the wall. But you can do it by putting straps in. So if you're a wall on top of a wall, automatically, if there's a region below, strap will go in place there for you. And what you can see here that in the detail report, you'll get, these are used for anchorage for the wall below. Okay, in the detail report, what you'll do is it'll give you strap information based on the region. So you're going to see tension forces here listed. The strap force right now is showing us as 4 kips. On either side here is giving me the actual strap force is 4 kips in tension. Okay, in compression, we're just going to be bearing, okay, but in tension, that's the strap force that you've got there. You can also tie a wall to columns below. Okay, just the only trick in doing that is you're going to want to double-click on that wall above and manually add those straps in so that it knows to pick up those strap forces for you in the detail report. Otherwise, it's not going to give you that because it doesn't find a region of a wall below it. Okay, but this one sort of gives us a good example of 4 kips applied, and then we see 2 kips and 4 kips going into this wall, 4 kips up and 4 kips down there. So you can kind of see how that teeter-tottering on that columns below shows us the information here. Another common issue or problem that people run into is aspect ratio. So you look at this wall here and you say, hey, I want to do a segmented design, and you run the wall and it gives you aspect ratio not met, can't do design. And that doesn't seem fair because it's very thin there. How do we get that to work? So a way to do work around that is just to say, let's draw the post and beam in next to the wall and just assume that you're just doing the lateral design on the R1 region here, or but by what we're doing, brute force is just telling the program specifically ignore that portion, and I'll carry loads down with the post, and then just design the wall portion over here on the right side. Okay, so that's sort of a workaround on a way to be able to build that. Another sort of common problem here is that when we have a soft story, okay, and what happens is the hand calculation doesn't always meet what our finite element model looks like. And when I talk about a soft story, what I'm talking about here is basically what we've got is sort of a stacked wall system, okay? We're doing maybe a discontinuous wall where things don't really line up, and we're doing a column on one side of this wall. This kind of example shows us here that this would be sort of what we would assume would happen in the hand calc method. We apply 4 kips, we see 2 kips up, we see an overall 2 kips down on this side, and basically we're doing statics to line this up. And that would be an easy way for your hand calc method to run. The problem is that the way to actually get this to work, we have to see that we're doing it looks like basically the model is not continuous over that in that section in the middle of that wall, and it's only connected to that one portion. So this sort of affects you in a lot of different ways, but most likely you'd be tying the wall together with those plates. So the plate elements on the top are connected to the plate elements on the bottom. And that's sort of where you'd end up typically doing. But what you'll notice is that we start to veer away from where the hand calc method has. So our calculations of our values are a little bit different. And what's happening is that you're going to be carrying your 4 kips through your model here and laterally and dragging it through. And the stiffness of these plates down on the left side is really going to drain out some of that load and pull it into this wall panel, okay, compared to what you've got over here. So we're seeing distribution a little bit differently between those. Now, what's important to note is that the strap forces between both of these situations, the upper walls do show a strap force of 2 kips on either side. So we're getting the strap forces here the way you would assume them to be, 2 kips carrying, 2 kips carrying. It's just that sort of the bleed of the load between this middle area of this wall is a little bit different than what you're expecting when you're doing a hand calc. The other issue is that if you really were thinking of it as this left portion and we tried to sort of model it that way to match a hand calc method, the deflection sort of goes haywire. You can see it's sort of letting go. Even if we just look at it visually, we can just see how it's just deflecting a lot differently from this model here. And probably not a really good assumption to sort of let these 2 plate models veer away from each other or separate like that. And lastly, if we kind of, this is sort of the tied together model, but this lastly, what I would even more suggest in this model is I would probably suggest in a fully pinned bottom. So you're really changing your forces even more by continuously pinning the bottom of that wall there. So now are we actually, not only are we changing things, we're going to be seeing a lot of different boundary conditions compared to what your hand calc method is. But what's right? Okay, it really comes down to engineering judgment, and only you can answer that question. How is your model being built in the real world? I think that's really one of the questions that we, as software engineers on this side, can't answer because I don't know how you're building it. Are you going to be continuously sheathing the top wall to the bottom wall? So you do make this sort of behavior come true where the walls actually behave together, or are you not? And then are you strapping it just with a single strap there at that end post? And that's the only thing that ties it together is on either side of the strap and the strap. Or do you get more of a multiple straps, somehow a way to actually get this to act compositely together? So these are the questions that you want to ask yourself, but also use the tools that are available, like the deflected diagram and displaying your joint reactions to understand how you did model it, and whether you model it the way you want to model it. Okay, so another problem that comes up is more of a discontinuous wall like this. So kind of an opposite shape, L-shaped wall, where we're carrying load from a smaller portion into a bigger wall. And how should we do this? This is a really good question because another question is, how are you going to build it? So the first part of this is, if we did this where we just carried the loads from that 4 kips directly to the lower wall, what we would be doing without just a default of draw a wall on top and draw a wall on the bottom, the results would show us is that you'd be getting loads transferred directly into the wall below. Okay, and what that means is that all the lateral loads will just disperse to the chords on the left and the right side. Okay, they will trickle down as a finite element analysis. They will come down and be distributed down, or we call it sort of smearing of the load into those 2 chords on either side of the bottom wall. Well, is that what you want? I have had a lot of folks say, hey, I don't build it that way. I always put a post there. Okay, so that's sort of another method of doing that. And you can draw in that post right there. One of the things by drawing in that post, you can say, I'm going to put a post element directly on top of that. And it will actually add into the model. What you can do also is make sure that post is a compression only. Do you really want that post to take compression loads and tension loads? So when this load gets reversed, this 4 kips turns in the opposite direction, would that post be in tension? Maybe not. Maybe it's just there for compression forces. So you can tail it to be compression only. Or you could have it be both ways. Either way. But then also maybe you add that boundary condition at the base of the wall. If you don't add the boundary condition at the base of the wall, what's going to happen is it will add some stiffness to this, but it will be part of the wall distributed loads there. If you add a boundary condition at the base of the wall, you're actually bleeding loads out of that wall on the lower level. Okay, so what you'll see when we look at this with the boundary condition there, we're going to actually see a lot more load pulled out of that model because of that post. So we're going to have different reactions there. Otherwise, we're just without that boundary condition. And now when I talk about boundary condition under that post, that is outside of the wall panel editor. Okay, so like I said, that is going to pull loads out or bleed loads out of that bottom wall. Okay, so it is something to experiment with. You also are going to have different chord forces between these 2 types of methods. So on the right side of there, we're going to have much lower chord forces on the bottom wall because we took it from the post. Okay, so you're going to see that. And also different deflections. This is a really important piece also to look at. When you put things in the model, add stiffness to that model like that, you're going to have 2 different types of deflections happening at the end of that. Okay, next piece that I see also a lot of times people have asked about force transfer and openings. What happens if you do platform framing? This kind of came up actually through one of our trainings. A fellow came up and talked to me through this type of a problem. And what we've got here is that when you're looking at the left wall, we look at this wall and we see that when you are doing platform framing, we're assuming it's going all the way to the top, full height for that framing. But when you do platform framing, you're actually sort of eating up a lot of the area that we would assume for the force transfer around openings. In particular, block number 4, we're assuming it to be real, real thick and deep, okay? And that means that it can take a lot of shear. But if half of it, or more than half of it, is actually the platform framing portion of it, and really you only have that lower portion of it available to carry that shear, you could have a failure because you didn't really anticipate that. So you have that much less of an area to carry that shear load. So what I would describe as a solution for that would be to adjust your opening height to include the depth of the floor framing. So we would do is we'd say, what's the depth of that floor framing? We would add that to the opening height on the bottom side here. So now we pop up that a little bit here, so we see that the opening goes way bigger. Our number 4 block region just got smaller, and that will reduce the portion of that wall above the opening, thus the amount of area of the shear forces. So that means that we took a huge chunk of 4 where it was carrying a ton of shear, no problems, and we just gave it just a lot less area for it to carry that, and now stressed out a lot different area there. Okay, so we can solve it sort of by opening up that area of the opening. And this might be something you might want to consider for force transfer around opening. This is really probably the only time that it really matters for its force transfer around openings. Because if you think about segmented, we actually take these sections and say they're ineffective. And for perforated, we don't really use those as well. Okay, so you really don't care too much about this big chunk unless you're in force transfer around openings. Okay, now let's talk a little bit more about our diaphragm loading here. So we were doing sort of single wall components, talking about that. Of course, all of these things will come into play when you're doing a building design, but we can take a closer look at actually how RISAFloor and RISA-3D will load up this for a diaphragm loading. Okay, so first thing I want to talk about when we do RISAFloor, this is a RISAFloor model that I'm going to open up here in a second. And what we've got is we define this diaphragm. We can do a rigid diaphragm or a flexible diaphragm in RISAFloor, and we define the diaphragm edge based on the slab edge. So there's going to be an outline of the slab edge around the entire building, and that's the diaphragm edge. And what you've got here, if we look at the lateral walls or the lateral system, are going to be what's resisting the lateral loads. Okay, so whatever is in red in our model is going to actually be defined based on that lateral system here of basically, you can call a wall a lateral system, you can call a beam a lateral system, or a column. And typically in our wood, we're going to be probably sending everything to be walls, to be lateral. But they're going to be resisting the lateral forces. So in this model, we can do is, first of all, talk about it as if it was a rigid diaphragm. And in a rigid diaphragm, we're going to be doing is we're going to be applying lateral loads in the x direction. And we can see in this lateral loads that we are applying it as 1 point load per floor level here in the x direction. This is a description of, it could be wind or seismic that we're talking about. But for a lateral diaphragm, what we do is we add that point load directly into the diaphragm. And everything we see here, all these little walls here, are actually going to be taking their level of whatever part of that stiffness is for this point load. Okay, so they are all basically contributing there, and the loads are going across the rigid diaphragm. They're going to be distributing based on their stiffness to the elements that are resisting. And that's our rigid diaphragm in the x direction. Same thing happens in the z direction, and we'll open the model and see how that actually works. But basically, that 1 point load applies into the diaphragm, and then we distribute that load based on its stiffness to the lateral resisting system, which happens to be wood shear walls in this model. Okay, for a flexible diaphragm, so there's actually an entity of a rigid diaphragm there. And internally, really, the way we talk about a rigid diaphragm is sort of just rigid links that tie everything together on that level. And then as you apply forces on that level in the lateral direction, they sort of distribute, everything distributes out to that, those walls there. So that's a rigid diaphragm. But a flexible diaphragm is a lot different than that. A flexible diaphragm, all we do is we take that same point load you see above there, and we just distribute it to the load to the walls resisting in that direction. So we don't see one point load anymore. We just see a lot of different distributed line loads at the tops of each one of these walls. Okay, we don't see, there's no actual diaphragm. Once you run the model, you'll see that the diaphragm is not there. It's not doing anything except just distributing the loads to those walls. And it actually does show you sort of here, this picture shows us any portion of that wall that's in the X direction will resist that. So these angled walls will get their portion of that wall, of that load distributed to it as well. Okay, same thing in the other direction. This is loads in the Z direction. And what we do see here is that we have loads applied distributed in the Z direction, and they are distributed. Right after solution, we see that they are distributed to the walls that are resisting in the Z direction. Let's open this model and take a look. So I'm going to jump into this model here. This is our flexible diaphragm. Oops, and I'm going to have to close this first. And don't save the changes. We're going to open this. Okay, so we're going to open up this wall model here. And it's just an example of kind of a simplistic building, but something maybe typical to what you might see as a building here. So this is our three-dimensional RISA-floor model. But and it's just one floor, just for ease to take a quick look at it. And if we run this model, it's actually got a solution, but I'm going to solve it one more time. You're going to post solution, we're going to run it and just take it into RISA-3D. So you use the director button. I go to RISA-3D. I have some wind loads already accounted for me here, 100 miles per hour, and we can see here the wind loads I've got listed below. I assume everybody has some familiar with RISA, and I've sent some notes to everybody, so if you do not, I do recommend that you take the tutorial and learn a lot more about how to go through each element here in RISAFloor and RISA-3D, but I want to make sure we get on the important pieces of how this affects our wood wall. So you'll see here we've got our forces in our X and our Z direction, and for seismic as well. I'm going to say OK. And we can look at this model now here, and we see that we've got, this is the model we've been looking at in our PowerPoint presentation, and I'm going to turn on these forces. And what I see here is if I look in the wind load in the X direction, this is what we were viewing. This is based on our rigid diaphragm, or flexible diaphragm, excuse me, is flexible right now. And the way I can double check what I have here is I can just quickly jump in and look at what's a flexible diaphragm and what's a rigid diaphragm. It's in my diaphragm spreadsheet. I actually can toggle this to rigid or flexible. So let's just go to rigid for a second. And we just see that the color changes based on whether it's rigid. And we see that outline of that rigid diaphragm in purple coming right across. So if I look at this model and I solve the model, and I say, let's solve it for a batch solution, and I run through, it's going to run through a lot of different load combinations. And let's see how many we've got, a couple here. And what it's doing is it's going to be going through and solving, and like we said, it's distributing it to those walls. But the other important thing to note for wood walls and rigid diaphragms is that rigid diaphragm at that wall, at the top of the wall, is giving the wall some rigidity. Okay, so it is actually giving the wall a little bit of rigidity. So it's not something to be unaware of, that how you've placed that in there. If I look at the deflected diagram, first I'm going to take a quick look at what might be the most worst case here for my wood walls, and maybe load combination, we'll say 15 looks like a good one to look at. So what I'm going to do is kind of view this model using my deflected diagram, going over here and taking a look at load combination 15. Okay, and I'm going to say maybe we'll amplify this by 100% here so we can take a quick look and maybe see something. Okay, so our model itself here is showing us that it's deflecting. It's basically all these 12 kips here, and we'll see. Let's see what load combination 15 actually look like, so we can see that for a second here. So load combination 15 had 5 kips running into it, but it had some nice dead loads in it as well, kind of to deflect this model. But what we see here is that the walls are all sort of moving together. and we've got deflected shape for this rigid diaphragm. Well, let's take a quick look also. This is an important thing to note, is that what I'm going to do is I'm going to take a look at that load combination 15 for a second here, and we'll look at what the maximum for this actually was. So if we look in the X direction and sort from absolute max to absolute min, oops, we're going to run down to 16. We can see here on load combination 15, what was the absolute max in the X direction? And that was 0.03. Okay, so not a ton of deflection happening. But what happens if we turn this model to a flexible diaphragm? If we switch it over to flexible, and I say yes, let's just take another run through it and see what happens there. This is where you really want to work with both types of diaphragms. You want to run one, understand which the worst load combination was, look at your results, and then come back ahead and take another run through it with flexible and see how it behaved differently. I would expect now once we run this flexible diaphragm, I ran through all load combinations just to help us see, but we probably could have just done 15. But I might expect to see a little bit of a different deflection. I should expect to see different load distribution. Well, the first thing I'll note when we're looking at this model is that instead of this load combination, we'll switch over to basic load cases for us. Instead of this wind load case in the X direction and the partial directions, what we got is that we got these transient area loads. And that's what I was describing here, is that for a flexible diaphragm, what happens is at the bottom of this load cases spreadsheet, you get transient area loads that are created for you. And they are 79 different basic load case distributed loads that got applied to the tops of the walls. These are not something you can affect here except by that basic load case, what was creating it. So if we see here, basic load case 8 was over here, basic load case 8, which was that single point load, turned into this transient area load on the top of each wall. And so we're looking at how these got distributed to the walls. Now there is no diaphragm except for this load distribution. So when we're looking at this, we see, let's take a quick look and if we remember what that load combination was, we said, so we'll sort this by absolute max to absolute min. And we can scroll down to the bottom at load combination 15, and we can see that we're actually getting a lot more deflection. How come? Because we don't have a rigid diaphragm. It's tying everything together, adding that stiffness on the top of that model. Okay, so right now, each wall is sort of just on its own. There's nothing but a wall with load applied to it on a flexible diaphragm. On a rigid diaphragm, you really can think of something sort of rigidly tying everything together. Okay, so it's very, very important to note the difference. Also, let's talk a little bit about here what we have something called shear load transfer between intersecting wood walls. So as I mentioned, you're not going to have as much out-of-plane stiffness as you have in-plane stiffness on a wood wall. Okay, what we've given you the ability to do is to say transfer those loads between intersecting walls or not. And when you transfer those loads between the intersecting walls, internally what that means is that your plates are actually connecting from one wall to another wall. This is a T wall here. And what we see is that each little node or plate element is tying in to the wall in the intersecting, in the T, in the upper portion of that T, okay? So you've got that, they're tying in, which means that it's adding stiffness in either direction for both walls. Okay, so do you want that? That's a kind of a question. Are you going to detail that wall so that makes it come true? When you're designing a shear wall and it meets an exterior wall, do you actually make it so that that ties in properly to carry the loads that way? Okay, I don't know. You have to sort of answer that question for yourself. And the reason is we gave you this nice checkbox so you can actually do that. The other thing, if you don't do that, what happens is you see that they are sort of don't interact, and you see these plate elements that are not connected to the T-wall. And so that you see that little gap there, it's actually sort of allowing it to flex beyond that. And that's going to basically have a different type of reaction between the two types of walls. And this is the type of question you want to ask yourself, and you can see I actually have a rigid diaphragm in this model that I'm looking at here. But rigid or flexible, those types of things. What do I want to be connected, and do I want them, if they intersect, to be connected automatically for me? That's a checkbox you can give it there. I already had mentioned this here, but lateral loads on the walls are created using these transient area load cases, and we see that here listed out at the bottom of all of my other load combinations. I see these transient area loads at the bottom there. So one of the things you can do, these are automatically generated for you. They're based on the upper loads here, basic load case, for example, WLX and WLZ. They're automatically created for you, but one of the things is they're automatically applied, and they're only for viewing purposes only. But one of the things I always tell people is if you want to take those loads and own them and change them, you can always go into that spreadsheet and copy them right out of there. Just use your Control-C, okay, highlight them, use Control-C, and then create a new load combination and just dump them right into that new load combination, or load case, and then take full power of them. You can change them, add to them, whatever you want to do at that point. There's not a whole lot of reason to do that, but there are times when you want to say, hey, I want to change that area load that was applied there, okay, for any number of reasons. Okay, so we talked about that, the diaphragm distribution. Now sort of the big finale is multiple story buildings. This is sort of a topic that comes up a lot, and this is a real good one sort of to talk about as our last model that we talk about today. When we're talking about multiple story buildings, a lot of times people are asking about deflection. How are you calculating the deflection for that multiple story building? You can easily lay it out, and you can model it in RISA-3D or RISAFloor. A multiple story building is not difficult, and we're seeing on this model here, I just applied some shear loads at each floor level. Okay, but what is going to be difficult is understanding how that behaves. So one of the things that we can do is let's open up this model in particular and talk through it a little bit. Actually, let me close down RISAFloor before we jump into that. And we're going to open up RISA. This is going to be called the multiple story building. Okay. So if I open up multiple story model, this is this model that we're looking at on our PowerPoint here. And what's important to note is that I'm adding shear at each floor level. So it just takes just a second here. My system's a little bogged down. But what we see here is that each floor level is going to be receiving some amount of shear. So if I ran, we're going to ignore this model, this portion on the right side for now. Okay, so if we look at this model, just this multiple story, and we see that I've applied some bed load, self-weight, live load is just some vertical load, and then some shear loads as wind loads. And if we solve this model, and we're going to solve here the model, I'm going to just solve maybe one load combination for shortness here so we understand it a little bit better. And I just solved load combination 9, which is just a wind load case here. Okay, so if I run that model, what I can do is I can take a quick look at this model. Let's first of all look at the deflected shape and understand what happens here. This is the deflected shape based on the finite element analysis tool. And that's something I hope that everybody takes out of this entire webinar, is that there are two types of things happening. There is a finite element analysis. It's based on plate elements. Our results that are looking at all the way up and down here are joint deflections. All of these items here are based on the finite element analysis of the plates behind the wall panel editor element. When we look at the detail report, we're typically looking at design information. So this is typically based on the code specifications. There are times, like we mentioned, that we're showing finite element deflections at the bottom of this, but we're typically most likely looking at things that came from either the NDS equations or things like that that were hand calcs like chord forces and things like that. Okay, so when we look at this deflection at the bottom of this wall, we see it's actually not that far off. It's got 0.379 and 0.337 for the finite element analysis. So it's pretty close. We could start to adjust that shear to try to make that match there, and that's this lower level. The next level we start to see is we start to see a little bit different numbers here, and I'm going to scroll down and see that. And what we see is that the hand calc method is 0.188, and the finite element analysis here is going to be 0.3. Okay, so we're starting to see a little bit of a difference. The one difference we do have for sure is that on this here, on this region, I can note that I don't have any hold down elongation values, okay? So it's right now it's just zeroed out. So that would be the one minor difference between that, and I just sort of built that side model just to verify that if I did have that hold down elongation value, which this one has it, and it has the exact same shear values there in the region. I can see I'm using exactly the same 0.75 shear. My total deflection is 0.25 in the wall on the right side. Okay, and so, but then this point, when we went to the larger wall, we saw on the second story that its deflection there is going to be 0.302. So still a little off, right? 0.25, which with the hold down elongation included into this equation, it is not quite 0.302. And then even above that, we see another type of difference here. We're going even smaller on the deflection, so even if we did add in the hold down elongation, we're still not getting close to that finite element deflection. And so we want to maybe start to work with this shear stiffness adjustment factor. So this is something where you'd sort of want to work with it. I showed here also on my PowerPoint, you can turn on your panel forces going to your uniform contours, and we switch over to FXY, and we can see how this actually looks. But one of the things that we might also do is turn on our deflected shape and really amplify it this time, sort of show it how it kind of really amplifies, and see sort of the difference of the two walls from one wall to the next. This wall here is just a simple wall, and we look at the wall to the left side in the middle portion of this wall. What's the big thing that stands out for you? It's probably the rotation is a huge thing that's happening. So we can see that this whole wall is sort of rotating as it moves up, okay? And this, when we tie it down and we do a simple single wall, we don't really talk about rotation, and we don't really worry about rotation. But that may be the difference between that finite element analysis model there and your equation value. There's a lot of little things that are happening in a finite element analysis here, versus your hand calc method, but rotation is definitely not included in that hand calc method. Okay, so when you look at this model, you really want to say to yourself, how is my model behaving? And I don't think I would want to even live with either of these numbers as a rock solid number. I wouldn't say, oh, for sure, I stake my life on the fact that the equation is right and I have 0.379 inches of deflection. There's going to be some things that happen and that equation is not taking into account. But I also wouldn't say that the finite element analysis equation is quite exact. But I, as an engineer, want to say to myself, okay, which one and which number can I start to understand and why it's behaving that way? And so you really want to start to say, let me look at this wall, how it behaves, and then now I can say, okay, yes, I see the rotation. I actually can go in and take a look at the joint deflections and see things like that to say, how is this actually behaving? We see X and it's actually going vertically, where this one is sort of planted. Maybe adding a diaphragm might be change things around a little bit, adding some stiffness, but really working with this deflection number to understand for yourself what is happening on each side. Okay, so that's kind of where I leave off on the multiple story. It's definitely something that I think that you should really question and understand yourself how your model is working. Okay, so what causes the difference between the FEM? I say here rotation, but then also what is really happening. And that's what comes right also back down to how are you detailing this model? How are you making it behave in the real world? Are you actually tying things together so this would behave this way? Are you continuously sheathing things across the wall heights? Maybe you're not, and if you're not, maybe then having them tied together like this might not be a way to do it.